Now we're going to discuss about the fifth chapter, uh, gate level modeling. This chapter describes the gate level modeling capability of Verilog HDL. It describes the available built-in primitive gates and how this can be used to describe hardware. So the built-in primitive gates include multiple input gates, multiple output gates, tri-state gates, and pull gates. Multiple input gate includes AND, NAND, OR, NOR, XOR, XNOR. Multiple output gates include buff and NOT. Tri-state gates include buff if 0, buff if 1, not if 0, not if 1. Pull gates include pull up, pull down. We have also MOS switches, CMOS, NMOS, PMOS, RCMOS, RNMOS, RPMOS, which is used in switch level modeling. Yeah, and bidirectional switches as train if one, R10, and R10 if one. Yeah. So, how this gate is used? So first we use gate type. So for example, we're using AND gate, so we will use and then instance name. So what instance one, suppose we AND gate 1 is a name which I provide, so it's a user defined name. And of course we need output terms, input terms. So in AND gate we have output and then inputs. We have one output and two inputs. So suppose output is out and input is A and B. So let's start with multiple gate input. First example is an AND gate. Example of these gates are AND, NAND, NOR, OR, XOR, and XNOR. So here is example. If you want to write how to declare it, we first start with the gate name. Suppose here is example 2 and RXB. Then we have the output and the X input. So we have to declare. Okay, so in AND A1 we have out 1, in 1, and in 2. So yeah, so one output and two inputs. In AND RXB we have multiple output and multiple inputs. It's a truth table of all these different gates. Then multiple output gate. Okay. So this one was one output and multiple input. So here RX1 STY is output and RIB, BRO, BRO, QIT, and FIX are multiple inputs. And now multiple output gates. So multiple outputs include buff and not. So what generally buff does is it passes the input signal, whereas not gate does is it uh, uh, negates the input signal. So same way it is declared as we have declared the multiple input single output gates. So we declared a gate and name buff, then instance name, and then multiple output and one input. The last one, clock and ready, are input signal and the rest are output signals. Then we have tri-state gates. So tri-state gate is a gate which has a controlled unit attached to it. So this gate models three state drivers. This gate have one output, one data input, and one control input. Yeah. So tri-state generally we start with the tri-state gate name, then instance name, after the output, input, and the control signal. So here's a brief diagram of the tri-state gates and the example of how these gates are to be it's initiated with the gate name, then instance name, and the output, input, and control signal. Here dbus is the output signal, mem data is the input signal, and strobe is the control signal. In buff 1 in buff 1 the control signal is like 1. So if the signal will only pass if the control signal is high. In buff 0 the signal will only pass if the control signal is low. Similarly in the case of not if and not 0, so in not if 0 the signal will is only pass when signal will only invert when the control signal is low. We have all these uh, truth tables. We have also pull gates. Those have only one output with no inputs. Then we have MOS switches. The MOS switches include CMOS, PMOS, NMOS, RMOS, RPMOS, RNMOS. These gates models unidirectional switches. So it's only one directional. That is, data flow from input to output, and data flow can be turned off by appropriate settings, setting the control inputs. So same gate name, instance name, output input, and control input. Here many examples are given. You can refer to the PDF. And we have bidirectional switch. Unless for switch level, for unidirectional switches, we have bidirectional switches, and the bidirectional switches includes TRAN, RTRAN, TRANIF, and then RTRANIF, TRANIF1, and RTRANIF1. And then gate delays. Now let us talk about the gate delays. We have already talked about delay before. Now let us learn about gate delays in more details. So generally what we do is we specify gate name and then delay. After that we specify instance name and the terminal list. So the delay is written is in three format: rise, fall, and turn off. If in case, now this is a brief table, I will explain this table right now. So suppose we specify one delay, only one delay specify. If no delay specified, there is no rise, no fall, no turn off, and turn off delays. But in case only one default is specified, one delay is specified, because here, as we have seen the delay syntax. Okay, we can specify one delay, two delay, or three delay in brackets based on our need. So only one delay specified, that indicates rise delay, fall delay, transition delay, and turn off delay. All is one delay, same delay. Then if two delays are present is mentioned, then the rise delay is the first one, the fall delay second one, and minimum of first and second delay is the transition delay, which is using like capacitance kind of circuit. A circuit which involves capacitance, and then turn off delay is the minimum for both. Whereas if in case of three values, then the turn off transition delay is the minimum of the three delays, but and the rest are in the order of which the delay has been mentioned. This is what the table indicates. An array of instance. We have already learned about how to initiate arrays. So in the first example, wire 3 0 3 colon 0 out in A and in B. So these three out in A and in B, these three are of wire data type, and each are of size 4 bits. So we can also declare multiple. We can also initiate multiple gates, such as we just have to write it once. Then we have we have more examples. Example of a decoder. We have master slave flip flow example. Please refer to the notes. And with this, we come to the end of chapter 5. With the next video, we will discuss chapter 6. Thank you.